Uh, so this talk is kind of a follow-up to a talk I had done earlier, just very briefly about this online class that I took recently, kind of December, January-ish. And I kind of wanted to share some of my learnings and like about the project I did for that. And then I also added some more things about kind of, instead of just about the project that I did, but also some of the things that I learned while kind of working on that project. And I thought that a lot of them sort of fell under this concept of, you know, what kind of as a web developer, stuff that I learned about embedded development. And I thought that was kind of an interesting perspective that, at least in the class, it seemed like not a lot of people were coming in from that direction. And so I kind of wanted to talk about that. So the general outline of it is I'm going to go over the project that I did, a little hardware timer project, and then kind of step back and talk more about microcontrollers in general, and then kind of just a potpourri of things that you have to kind of deal with or consider when you're doing embedded development. And then there's some correspondences between little bits and pieces in embedded development and web development that I kind of noticed going through things. Then I'll talk a little bit about what it takes to take your project from a prototype to kind of a more, if not production ready, sort of a version 2, make some custom hardware. And then lastly, I'll talk a little bit about kind of wireless connectivity and IoT and some interesting areas that I think embedded development is going. So that's kind of the schedule. So very briefly, the Pomodoro technique. So it's this, I would say, sort of getting things done technique where you, depending on the day, trick yourself or just agree to work for pay attention for 25 minutes, you take a break, and then you repeat that cycle. And then when you've done that 4 times, you can take a longer break. And it's just a way I find when I basically know what I need to do and I just need to sort of buckle down and do it. I find it can be a pretty handy technique for sort of getting more accomplished in the same amount of time. And yeah, one of the little tidbits, it's tomato in Italian. So my concept for this project was to take one of these sort of desktop reorientable timers and kind of do my own spin on it. Nothing super fancy, but it was good to know that there was some prior art here, that I wasn't just making this up. And it seemed achievable in the, I don't know, 5-6 weeks that I had to work on it, as well as like learning things along the way. First thing I did is I went out and got this dev board, and I considered a number of things, but I knew I wanted an accelerometer because I wanted to be able to have this thing sensitive to which direction is down, and which is when you turn it on the side, that it can see that you've done that. And accelerometers and gyroscopes seem to come in pairs often, and the gyroscope can also be handy for knowing when there's actual motion or when it has stopped moving. And so that I didn't end up using it, but it can be helpful to sort of improve the accuracy of the accelerometer. It's sort of complementary. And then this dev board just happened to come with like a lot of wireless connectivity and just a bunch of other peripherals. And I think this thing was about $60, and there's a whole heck of a lot of documentation about like STM32 family of chips online. So it's kind of good to get something that's well supported. So some of the things that I looked at in particular is a Cortex M4, which is a relatively powerful chip in the kind of Cortex family. There was 1 megabyte of flash and 128K of RAM. And having looked at this stuff for a while, this all kind of was like, wow, that's a lot. But, coming from a web background, at first sight, you can kind of think, well, geez, 128K of RAM is not a whole lot at all. That might just be a few images on a web page. This also included some communication features. I'll talk more about these later, but these are various like serial communication lines that it has. So SPI, I2C, I knew I was going to have to use. I initially tried to use USB, but I kind of cried uncle on that for mostly reasons of just not having time to get it working. And one of the things I wanted to take it, or one of the directions I wanted to go, was to add some Bluetooth support. So I wanted you to be able to kind of categorize the tasks that you are working on into different buckets and be able to use some sort of app to set that. And then, like I said before, the gyro and accelerometer. And then it also had things like temperature, humidity, magnetometer. There's a whole bunch of other kind of cool stuff. So yeah, this is a picture of me trying to debug my drawing code. And so this was a big celebratory picture after I had struggled with this for quite a while, and then finally got it to draw a circle on the screen. It took a lot more poking at it than I initially thought. Okay, and then before I talk about the firmware, I wanted to just show a real quick video about the project. Part of this course, we recorded a short video about using it. So I'll just play this.
Hello. So this is my desktop Pomodoro timer for the Red Jellies cohort. So there's just a few functions that this will do. So it's orientation sensitive, so that when you tip it up, it will start timing down your 25-minute Pomodoro. If you want to abort that somewhere in the middle, you can press this blue user button and it will cancel out of that. Each edge represents a different timer in set. So here I have a really short break timer just to show kind of what happens when you're done. And so when you set it back down, it will revert back to the overall Pomodoro count. So of course, if I were to let this go for the full 25 minutes, at the end of that, it will increment the Pomodoro count and you'll end up back at the kind of overall statistics screen. Yeah, so that is really what the project does. Thank you very much.
Yeah, so that's basically it. Yeah, sorry you couldn't hear that, but I was pretty much just saying, that when you tip it up, it starts timing, and then if you hit the button on it, then it will reset the timer, and if it counts through a full Pomodoro, then it increments the overall count that you've done. So pretty straightforward, not a whole lot of functionality. Part of what I wanted was it to just be not have like a lot of settings, that you pretty much just can pick it up and put it down and have it start timing for you, and not really dictate like how you have to take your breaks or anything like that. You can, you're always free to orient it however you want. So the firmware is basically a big state machine that you can be in this waiting state where it's reading the accelerometer from time to time, checking to see if the orientation has changed. And then if it has, depending on which way you've set it down, it will jump over to one of these timing states, and then it will basically just fire off a periodic timer interrupt, which I'll talk a little bit more about interrupts in a few minutes. But it will kind of count down, and then when it gets to 0, it signals that the timer has elapsed, and then it resets itself and then shows off the statistics and then kind of goes back into the wait loop. And then it's not really shown in here, but then there's another path where pretty much at any time, if you hit the reset button, it'll just go right back to resetting and then show stats. So kind of just a pretty straightforward. And then I translated this to basically a big switch statement. Yeah, and so this was the IDE that I was using to develop. So you don't have to use like the manufacturer IDE. I did in this case because it had some handy features. Like one of the things that you could do was have the IDE sort of generate a structure for you that you just kind of plug your code into. And it had a little configurator tool where you could say, okay, I want this pin to do this function, and please turn on USB, like that kind of stuff. And it would generate the code and sort of dump it into the project for you. And then all you had to do is kind of include the headers and things like that. So it sort of made getting up and running easier. But it was a little awkward to work with initially because there would be these comments, and you're sort of only allowed to put your code inside of these sections. Otherwise, the sort of auto configuration tool might write over your code. So you just had to kind of be aware of that and kind of plug your stuff in where you needed to go. There's a way where you can kind of set it up with the IDE and then click a button and say, hey, please just spit out a file with like makefile, or spit out the project with a makefile and leave me alone kind of thing. But more or less, this was okay. I mean, it's like an Eclipse-based IDE, and so it wasn't too horrendous. Yeah, so my code was laid out. I tried to have like a very sort of strict layering of things. Not always successful, but I wanted for instance, like my drawing code to just depend on the display driver, and then the SPI connection, and then finally onto this STM32 hardware abstraction layer, which was kind of the lowest level code that talks to the hardware. So by keeping it in these well-defined layers, it was easy to kind of make some change lower down without having to alter my main code very much. So I had, in my main function, I had nice things like, draw a circle, or, write this string to the display, and the underlying code layers were able to kind of figure out how to do that. And then BSP, you'll see that term come up a lot. It simply means board support package. And so the idea is that you are sort of bundling up all of your code that is specific to the board that you're working with into one module, so that you could conceivably switch that out, and you write all of your higher level functions in terms of those like board support functions. Yeah, and then I basically just had a big main, which was driving all of that. Yeah, so the enclosure, you saw it a little bit in the video. This is my like really, taped together foam core from like the hobby store, just put together. And I just wanted to kind of prototype out this triangular shape that I had envisioned. And so you could stand it up and you could rotate it. And then I had also done some 3D modeling to sort of plan out what that would look like if I were to 3D print it. I haven't ended up 3D printing it yet. I'm sort of planning on doing a version 2 that I'll talk about in a little bit. But it was kind of fun to design different ideas for the case. So this is me using OpenSCAD, which is kind of like a scriptable 3D modeling program. And it's also kind of interesting just learning about what can't be 3D printed easily. So I kind of learned about the no overhang rule. Yeah, so that brings us to talking about kind of what microcontrollers are in general. Now that you've seen my project, what are these little guys about? Oh no, this guy's supposed to run like a little bug. Okay, there we go. Yeah, so what are microcontrollers all about? So this is my super duper simplified architecture of a microcontroller. And I guess the overall thing to note is it takes all of the kind of parts of a computer that make it work and sort of bundles them all together for the most part in one chip. And so you have a processor, you have the memory, it has storage, and then it has various peripherals for talking to, so either internal peripherals or interfaces for going out over the wire and talking to some other chip or something like that, like some of the serial protocols that I'll talk about. And so the gist of this is that you don't need a whole lot of supporting circuitry to make a microcontroller work. This might look like a bunch of stuff, but some of it is not necessary. And some of it is kind of just other supporting chips that do other things like regulate power and things like that. But more or less, you can kind of just feed a microcontroller power and ground, and it will sort of be good to go. It's more complicated, but not a whole lot more complicated. And one of the defining characteristics, I think, of microcontrollers is this notion of memory mapped I/O, where there's a physical place in memory where if you write bytes into that, it will cause some behavior to happen on the chip. So if you write a 1 into this area in memory, then circuitry will convert that memory write into an actual, the pin will go from 0 volts to 5 volts. And the reverse is true. You can read the value of a pin into memory, and it will appear from a place in memory, or it'll appear in a place in memory that your program can read from. So it's kind of this circuitry that converts back and forth between memory locations and actual physical actions that I think kind of makes microcontrollers a little bit different from programming computers, that you're actually thinking about making, bits happen in the real world. Yeah, and so there's just a whole bunch of different topics in embedded development that kind of, as I was doing this project, I came across. And so this is a little bit of a potpourri, but most of these things in this section were things that I encountered or had to learn about kind of to do my project. So the first thing, and it's almost like step 0, is that to write programs for this little ARM chip, which does not run x86 code, you're going to need not just a regular compiler, but you're going to need a cross compiler. So it's sort of brain twisting the first time you really think about it, but it's a compiler which is written for your computer, like your x86 or M1 or whatever. But instead of spitting out code that will run on that same computer, it spits out code that runs on a different computer. And so you take your high-level code, like C code or whatever, and you run it through this cross compiler, and out pops an ARM executable. And this is a totally different architecture. Like if you try to run this program, it just, it fails immediately. It's not at all the same. And so then you have some means of, once you've compiled your program, you have to get it onto this external chip. And so there's various ways to do it. The one that I was working with happened to have USB. So I could just directly copy over, the IDE could copy over the compiled program over a USB connection and put it onto the chip. You might have to have like a separate device, which on one end talks USB, but then on the other end talks some custom sort of MCU thing like JTAG. And this is variously known as like a debugger or a flasher or something like that. And this is like a picture of that setup. So on one end, it's connected to the computer over USB. And then on the other side, it's got this, funky ribbon cable that plugs into the board. And yeah, so the other thing that this device will do is it runs GDB. And so besides just putting your code on the device, you can also debug the code while it runs on the device. And so on your desktop, you connect to a GDB server that behind the scenes is talking over this JTAG link directly to the board. And you can do things like pause the execution and step through memory and do all sorts of stuff. The other thing that I had to kind of grapple with is when I was writing to the external LCD screen, that involved sending serial commands over SPI. And so this is a snapshot of some bytes being sent over the SPI connection. And this, I'm using a device called a logic analyzer, and it basically is like a, if anyone knows what an oscilloscope is, it shows different voltages over time, but this is specially designed to kind of work with digital voltages. So that's why these lines are all very crisp. It's basically just saying, yes, there's a 1 or a 0 on the line at that time. And so it can actually look at the communication as it goes over this SPI connection and show me the bytes in real time. And so if you recall earlier, when I had all of these probes connected, this is actually what I was looking at. I wanted to see if I was sending the correct commands, and this is writing individual pixels to the screen. And for a while, that was not working at all. And so I picked up this device to be able to kind of snoop on that and see what was really going on. Yep, and so all these little kind of connectors are the actual logic analyzer probes. You can kind of see it in the background there, but it's not a very good picture. So I've talked about SPI or SPI a bunch of times, and this is what I was looking at. It sends bytes by toggling various pins at the right time. And the thing to notice here is it sends along a clock signal. And so you can see every time there's one of those rising edges, it will check to see if there's a bit there. And if the bit is high on that MOSI line, then it's a 1. And if it's low there, it will be a 0. And so this is what it would look like sending the byte 0xAA, which would just be like 10101010. And so SPI is good for kind of high speed connections. Another really common serial bus that I did not use in this case, I guess I did it for debugging a little bit. You can do like printf debugging over UART. And UART is pretty similar to SPI, except you notice there's no clock signal. And the other thing is the bits are in the other direction. So this is least significant bit first. So this is kind of like backwards. And I actually might have mislabeled that. This might be 5.5 because of that. But anyway, so that's what it would look like to send some serial data. And the other thing to notice is because there's no clock, both sides have to agree ahead of time how many bits per second you're going to send. So if you've ever seen like Telnet or things like that, where they are saying like 9600 BPS, this is where you have to specify that. It's a very common protocol just because it's very simple. Okay, so another common embedded topic is that of clocks. There was a lot of fiddling with clocks. And one of the things that I liked about using the IDE, or at least was super handy, was they have this kind of configuration panel for setting up all of your clocks. And usually what happens is these chips will have like an actual quartz crystal somewhere on them, either external or internal. And then they do various divisions or multiplications of that clock signal to get the various timers for different systems. So this chip ran at 80 megahertz for most things, but you could derive either faster or slower clocks for certain peripherals that needed it. And but suffice it to say that a lot of what you kind of are concerned with is timing things. I've heard it said that microcontrollers are just like really fancy clocks, that most of the things you're doing with them, you're using a microcontroller because the timing matters. Some more peripherals that I dealt with. Buttons and things are connected up via GPIO or a general purpose input output. And this lets you toggle input pins, light up LEDs. It's really common. It's kind of the hello world of microcontrollers. Another common function is converting digital to analog or analog to digital. So either reading a voltage on a pin or driving a pin to a specific analog voltage. DACs are less common, and I tried to research why this is exactly, but you definitely notice it, that like you'll look around for a chip and, like a $1 chip will have an ADC, but then if you want a DAC on a chip, suddenly it's like a $15 part or something, it's some sort of more specialized kind of signal processing chip. So you can get these external digital to analog converters, and that's what's in the picture here. Another common peripheral that I did not know very much about is called PWM, and it stands for pulse width modulation, and it's sort of a way of having a digital chip kind of fake out an analog signal. So you can see the blue signal in the background is this, it'll be a digital signal that's toggling on and off at some fixed frequency. And what you can vary in software is the width of that pulse. And so sometimes the pulse will be longer in duration, or sometimes it will be shorter in duration. And if you filter that a little bit through like a capacitor and resistor, it will kind of approximate an analog signal. And so like if you want to dim an LED, or if you want to drive a motor where you want to be able to like increase the brightness of the LED or speed up or slow down the motor, you'll sometimes just drive those with a PWM instead of the expensive circuitry that you would need to give it like a true analog signal. So I use this on one project to output like audio, and it actually works pretty well because these pulses can happen really fast. Like you can run these pulses at like 80 megahertz. And so you can kind of derive the analog signal that you want. Another topic that comes up once you start thinking about this really ever-present idea of interrupts is of context switching, that in a microcontroller, unless there are ones now with like multiple cores, but typically they're just a single core. And so it is really, it's like 1980s hardware, that you'll be doing one thing and then this event happens, like a timer goes off, and the CPU will save all of your registers. It'll kind of like stop your program, and then it will jump into this other code somewhere else. It will do whatever it needs to do in that interrupt, and then it will restore all of your registers and put your program state back, and then jump back into your code. And when you can achieve all kinds of interesting things with this. Like you can have an interrupt that goes off when somebody presses a button, and then you basically write some callback code to handle what you want to have happen when that button is pressed, or when a GPIO pin goes high or low, or just a timer, like every 10 milliseconds, you want a timer to go off, and then you can do something in the interrupt. And if you kind of keep following this idea along, you can even use this to simulate running multiple things at the same time. Just to not overload words, I didn't call these like threads, but you could think of these as being like threads of work, where you have these different tasks that you want to kind of, quote unquote, all run at the same time. But in reality, what you're doing is you're running a scheduler periodically, and depending on various priorities or what you need to get done, or just maybe it's just round robin, one after the other, you stop that task, you load up a different task, and then you start doing that for a little while, and then again, hop over to the scheduler and kind of continue. And if you kind of keep going down this road, you end up getting what's known as RTOS, or real-time operating system. And so you can think of it as the kind of most stripped down, bare bones version of an operating system, where it's really just concerned with running these separate tasks and scheduling them. Maybe it'll have some functionality around sending messages between tasks. So it might have like a queuing system, or mutexes to kind of protect shared variables, things like that. And so instead of writing, like I did, I wrote my program just as kind of one big state machine. You could instead write this as like separate tasks that each are kind of just looping forever, doing their one little subject, and for more or less being able to ignore the existence of any other task. And so I just linked this page because FreeRTOS is an open source project, but I wanted to point out that like AWS has, they have kind of a customized version, sort of in the same way that they customized Linux to run on EC2. They have this customized RTOS to run on their like cloud system. And so if you get to know FreeRTOS, presumably you can use like AWS backend servers to upload data or do other things like that. And RTOSs are really helpful once your programs start to get more complicated. Once you have several things kind of running in the background and you don't want them to get delayed or like miss a step or something like that. A really common example is once you're running some kind of networking protocol, once you have like Wi-Fi or Ethernet or something like that, you want to make sure that those packets keep kind of coming in and going out, and don't get held up while your chip is doing something else. Yeah, so some of the correspondences I noticed when I was working on this project. The first is, this was really apparent to me kind of early on, that like kind of when I squinted at interrupts, it was like the terminology was different, but this looked an awful lot like async or callbacks to me, that you have some main code that runs, and then you sort of register a handler to run when some certain condition happens. And it's just in JavaScript, you may just do like a set timeout, whereas on the microcontroller, it's the actual hardware is managing that, or maybe like you've received a byte on UART or something like that. And so like the context is a little different, but the concept I felt like was pretty similar. So yeah, so here like a timer expires and then you jump into this interrupt and you do something, and then yeah, it looks a lot like an async callback, even down to, oh, misspelled that, even down to just like you have to be careful about sharing data between the callback and your main code, and the fact that you can't just like return a value from your interrupt. You have to kind of pass it back into your code in some other way. Maybe you set a flag or do something like that. Linking and bundlers. This was like a little bit more obscure, but a lot of times on microcontrollers, they'll have like a little bit of memory, and maybe then they will have another chip that has like a little bit more memory. And maybe they'll have an external flash chip somewhere that has even more memory. And so unlike a desktop computer or your laptop or something that more or less has a whole ton of very homogeneous memory, on a microcontroller, it's much more mixed, that you might have all these different chips in all these different places, and you have to kind of decide where in the memory space you're going to map those things. And I felt like this was a little bit like working with a bundler, where you kind of had to choose your modules and have them linked together in a way where the browser could actually run them. Yeah, and here I was just pointing out that you also, when you want to debug something on a microcontroller, you recall that this is not going to be the instruction set of your architecture. So this is ARM opcodes over on the right. So this isn't anything like x86 opcodes. And so if you want to be able to debug, you're going to have something that's kind of akin to like source maps in JavaScript, where if you are kind of transpiling your TypeScript code into JavaScript, you may also want to have a source map around that can say, okay, well, line 100 in your original source code maps to this line in the kind of compiled version, or minified or something like that. And so you have something very akin to that with like debugging symbols, and then being able to step through it in the debugger. Yeah. So the other thing that I started to kind of play around with is almost as I was working on the prototype version, I started kind of poking around at thinking like, oh, hey, maybe I could make this into sort of a more standalone device, that instead of using like a $60 dev board, maybe I could just buy a chip and, like an accelerometer, and kind of build my own custom printed circuit board. And so here I'm using a program called KiCad, and it's like an electronics computer-aided design package. And so what I was doing here is kind of hooking up that supporting circuitry for this is a different chip that I was using. This is I think it's like a Nordic chip that has Bluetooth natively on it. And so I'm kind of hooking up the supporting circuitry around it. Mostly so far, it's like debugging headers, and I was going to put USB on there. But this is kind of what designing it looks like. So you draw the schematic, and then when you've drawn the schematic, it dumps all of those components kind of into another part of the CAD program. And this is where you're actually like laying out where the chips will sit on your printed circuit board. And so this is this is not very far along, but the idea is it's like a little jigsaw puzzle, and then you have to kind of play a big game of connect the dots to put little copper traces between all of these red pads. So every time there's a resistor or a capacitor or something, you have to kind of click in there and drag a line from that to the next place that it has to connect to. And when you've done all that, you can send it off to various websites that will print that out on a circuit board and etch it and then mail it back to you. And so it's kind of fun to do this. So you can make your own printed circuit boards pretty economically these days. Like they'll be a few days and under like $10 or something. So at least in small quantities. So yeah, it's kind of fun. I find it kind of like knitting or something. It's very relaxing to sort of like try to connect all these traces together.
So Chris,
yeah,
hate to put a damper on your knitting, but doesn't KiCad have an auto router?
It does. Okay. And I've even tried to use it on occasion. And
yeah, usually sometimes it'll leave you with 2 or 3 traces that are a nightmare, but
okay,
it's way faster.
Yeah, I've had mixed results, I guess, but that's good to know. I mean, it's okay, totally.
But if you're happy to knit, you be you. So
well, that's good to know. Yeah, I'll have to try it out again. I know I've done it in the past, and it was it kind of made things sort of difficult to untangle, but I'm like KiCad is improving all the time. That's kind of the big open source project in this area. So yeah, that's cool. I'll give it a shot. Sort of to kind of round things out, I wanted to talk just a little bit about IoT and wireless. And I think it bears talking about a little bit, just because I think this is one of the areas that has kind of changed recently and has made, I think, embedded development have kind of a different spin on it. I think kind of earlier, it was much more common to have like an embedded device that, it is wired rather than wireless. And now it's much more common and it's lower cost to get these chips with some kind of built-in wireless connectivity. And you basically have your choice of, whether you want that wireless to be very low power, longer range, higher bandwidth. And there's lots of different protocols and kind of networks that serve as kind of the, connection medium that you can use. And, once you're able to do this, you can potentially have low powered battery or solar devices out in the field collecting data close to what it is that you want to monitor. And I think this really opens up, especially in sort of commercial and industrial areas, a lot of opportunities for kind of increased efficiencies or, just being able to like capture data that you weren't able to capture before. And just as an example of the sorts of things that are out there, this is like, this is a little cellular module that connects to 5G, and from your microcontroller, you just send little JSON packets to it, and it takes care of sending that over, like a cellular connection. But there's lots of other devices out there. So Wi-Fi is pretty well known. And I like this chart because it kind of shows a few things at once, that there are these sort of non-overlapping regions of different kind of wireless protocols and frequencies. And although it doesn't say it, but bandwidth roughly scales with power usage as well. So that Wi-Fi and mobile internet like 2G, 5G are relatively speaking more power hungry than some of these other things like BLE or LoRa. I don't really know too much about Sigfox, but I know it's one of these more like long range, low power, but also very low data rate connections. And then, once you have this connectivity, kind of on top of that, you can have various kinds of sort of backhaul networks. And so, you're here, I've read a little bit about LoRaWAN as kind of a connectivity sort of back end where you can network devices together and then at some point connect that to the internet to kind of get your data back to where you want it. And then similarly, you can use like a cell phone provider to provide data via something like 5G or LTE or something like that. And yeah, both of these are available as like commercial services. And I recently heard that I think it was like Comcast or something has like a LoRaWAN service. So it's definitely out there, and there's various different projects in this area. Yeah, and so kind of all of these things put together is, Internet of Things. And the reason I made this slide was kind of just to be goofy, but a lot of what we see is kind of the consumer side of things. It's like a network connected, speaker or something like that. But I think as I've learned more about this area, I think the real big driver of it are sort of commercial and industrial uses that while it's kind of a novelty to have like light bulbs or something that are connected to your cell phone, it makes a whole lot of kind of like business dollars and cents to be able to like capture data, in like medical fields or agricultural areas. And so that I think a lot of this market and a lot of the kind of driver of some of this direction is those industrial and commercial uses. And it's less obvious because as the end user of whatever service is kind of enabled by that, you probably don't see it as much. But I think it's kind of the bigger, it's sort of the iceberg that's under the water. So yeah, kind of in conclusion, some of the things that I learned about on this this journey is I learned to kind of put a little more focus on design when I'm working on this kind of project. Not a total like, waterfall is best kind of thing, but there are things to consider when you're going to develop some sort of hardware device, in that you may have to kind of set envelopes for various capabilities and requirements that you need. Like I knew I needed this accelerometer, otherwise kind of the project is just not going to work. And so that limited me to certain chips. And, if I wanted something to be battery powered, like I think I do on this eventually, I'm going to have to consider like how I write my code and what kind of devices I use. And kind of the moral of the story is that if you don't consider these up front, it can be really difficult to work on them down the line. You might be sort of hemmed in by choices you've made earlier on. And as far as coding, if you have good layering and interfaces and kind of appropriate abstractions, you can hopefully insulate kind of your business logic from these lower level kind of interfaces and drivers and things. The other thing that I think is kind of cool is that I did do this project in C, and C++ is very common. But increasingly, I think other languages and environments are making inroads into embedded development. And I think this really helps with kind of the approachability of things. That, I mean, Arduino has been around for a while, and I think behind the scenes is actually just C++. But there's CircuitPython and MicroPython now. There's a Rust embedded project. Some microcontrollers can run C# code. And there's lots of other things out there if you kind of look around. And so kind of the combination of microcontrollers being a lot more powerful these days and power efficient, you're able to run runtimes and things on them that previously wouldn't have been within reach. And so I think that's kind of cool, just because I think that will really bring more people in, and it makes it a little bit less mysterious. So yeah, I think that's about it. I have a bunch of resources on here. I'm sure I'll post these slides. But yeah, that's if you want to reach out and say hello, some email, GitHub, Twitter. Yeah. So thanks a lot for coming.